The first two examples that we'll look at involve calculating the net moment on an object as it is subjected to various forces at various locations. Notice that these two forces on the left will generate a counterclockwise moment collectively, and this force on the right will generate a clockwise moment. We can see that as a positive number for each of those moments from the left and a negative from the right. In order to calculate the moment, recall that the moment formula is plus or minus the force times the perpendicular distance. Now, the perpendicular distance refers to how far each of these forces' lines of action are from the point of rotation O here. Well, the first force, 200 newtons, is actually 4.2 plus 1.2, or 5.4 meters away. The 300 Newton force is only 1.2 meters away. Collectively, their moments are positive since they generate a counterclockwise rotation around this point. That is, if you were to imagine these pushing down, this object would topple over to the left, or anti-clockwise. This 270 Newton force will induce a moment on the clockwise direction. Now, that moment therefore is going to be negative, and its line of action is 3 meters away from the point O. And when we total all of these contributions, we get a net moment which is positive, 630 Newton meters. And this is therefore a counterclockwise moment. So if we press play on this entire configuration, the net moment would be in this direction. One comment about your assignments is that some of you wrote down newtons per meter as the units. This is incorrect. The units should be Newton meters. The next example is similar to the one we just covered. Notice that in this situation there are again three forces. However, their directions are not necessarily the same as the previous example. This direction is still going to be downward and will therefore have a counterclockwise moment induced by that force. And this force over here will also induce a counterclockwise moment since it's acting upward. That's indicated by the two plus signs here. Finally, this 300 Newton force will generate a clockwise rotation and therefore is represented by a negative here in the moment expression. Each of these forces have lines of action, and their lines of action have a respective distance away from the point of rotation O. For example, the 250 Newton force is 5.1 plus 1.3, or 6.4 meters away from the point of rotation. The 300 Newton force is only 1.3 meters away from the point of rotation, and the 250 Newton force is 3 meters away from the point of rotation. When you see a question like this, you can intuitively maybe see which way it's going to go overall, but you don't have to think that far ahead. In fact, if you're good with your numbers and you don't mess up the directions, you should figure it out regardless. And in this case, the net moment is positive or counterclockwise. So if we press play, so to speak, on this situation, this object would topple over in the counterclockwise direction as indicated on this figure. In the next example, we're not looking for things to topple over. We want equilibrium. So how is equilibrium achieved? Equilibrium refers to when the net moment is zero. What does that mean? Well, it means if you take the contribution of the various objects in this configuration and compute their moments around the point O, or in fact any point along the structure, we would have to see a net moment of zero. It's useful to choose O as the place where we want to find the net moment for, because there is a reaction force that's acting here. We're not going to cover reaction forces in this unit, but we will cover them in the last unit. That's to follow this one. So let's calculate what the net force is. Net moment is, excuse me. Notice that we assume that this beam here, this object, has a negligible mass. So we have a 20-pound force, which essentially is imparting a force that's downward. of 20 pounds. And we have a 40-pound force, which is imparting a 40-pound force down there. So the question here is to find the distance x so that we can have equilibrium. And we can do that by adding up the moment contribution of each of the two objects' weight. Notice that the 20-pound force is 4 feet away from this balance point. There it is. And its moment is positive because it's counterclockwise. And the 40-pound force is inducing a clockwise moment as indicated on the figure. It's very important that you keep track of the signs. Notice that the minus sign here is going to be very important algebraically to produce a positive answer for x. And the numbers are very simple here. I should mention that an example such as this does not need any fancy mathematics or physics to solve. You could give it to someone probably in the middle school and they would be able to solve it based on some common sense or some logic about levers. The next example introduces another mass, and you can see here the 30-pound mass. All it does is add more terms to the equation that follows below. So I leave that one to you to look over again. Essentially, there's a middle term here that is due to the introduction of the moment that the 30-pound force introduces. In contrast to the previous example, the solution, or the value for x, I should say, is 3.5 feet, meaning that this 40-pound mass has to be further along the beam in order to balance out the other two masses. I'm not the best at drawing here, but imagine that you had a seesaw and you had two kids on this side, and yes, they have arms and legs there they are, and you would need this kid on the left, assuming they're all similar mass. This kid's got to move further out as you have an extra person on the seesaw. The next example is similar to the previous two examples. However, in this case, we're not interested in finding the location of where the force is placed, but what the actual force should be in order to have equilibrium. So, if we were to look at equilibrium about this point O here, we would notice that the 600-pound force induces a positive moment, and the force F induces a negative moment. And there they are, positive and negative. Similar to the previous questions, you can find the moment of this force here, which would be 1,200 pounds, there it is, and the moment of this force here, which would be negative 5F. There's your negative 5F. If we move the negative 5F to the other side, we can divide out and get that the force must be 240 pounds to achieve equilibrium. I encourage you to try these questions in the notes on Blackboard, and hopefully you can build a pattern based on the previous few examples. Well, here's another one of the same situation. And this time I've put the variable force here on the left side, but algebraically it comes down to balancing out its contribution and the contribution of the 600-pound force on the right. So it's time to move on to some more advanced examples. So let's see how we do. This next example is a bit more tricky. The objective is to find a single force F, let's say it's here, so that it produces the same moment as what the individual forces represented here would. We also are interested in what that force F would be in terms of its distance from A. So the objective is to find out XA and F. Well, F has to have the same total as the two downward forces. So F is very quick to calculate. Notice that F is a vector, and I've indicated a downward direction. Next, if F is to produce the same moment as the original two forces, we could calculate the moment of the original two forces and equate the moment that F produces to that moment. So, here's the moment about A by the individual two forces. It's negative. It's negative because both the 6.9 and the 5.8 kilonewton forces produce a negative moment, or clockwise. And there they are. The 6.9 kilonewton force is 6 meters away from the point A, and the 5.8 kilonewton force is 6 plus 4, 10 meters away from the point A, its line of action. Next, The moment generated by F is given by F times its distance, xa, and a negative sign also because it is clockwise. There's your negative sign. This number here represents the actual magnitude of the force, and xa is what we're solving for. So, simply set this equal to this. And when you do that, with some very quick algebra, you should be able to get the answer of 7.83 meters. This example is an extension of the previous one. I simply have added another vertical force, and it's in the upward direction. So we are trying to replace all three of these forces contributions with a single force. Now, does this force act up or act down? Intuitively, you can tell by just kind of checking the numbers here and seeing which is more. Well, which is greater. Notice that we have, this is definitely more than 10, so that's definitely going to go in the downward direction. I didn't actually do the mental math there, I just got a quick estimate. So we know that we can assume that the single force will be downward, and we'll call this distance xa as in the previous example. To calculate F, simply add up the individual forces. Notice that we have 2 acting down and 1 acting up, and therefore the net force will be 7.1 kilonewtons downward. So, where do we place this force so that it produces the same moment as the 3 individual forces originally? Well, let's take a look at those forces. I'll just highlight them here for a second. So the 6.5 kilonewton force is over here, and it produces a negative moment because it's in the clockwise direction. The 4.8 kilonewton force is over here. It's also producing a negative moment, but the 4.2 kilonewton force is producing a counterclockwise moment, or positive. So the net moment caused by all three of these forces is negative, or in the clockwise direction. Similar to the previous example, we can calculate the moment caused by F about A, and there it is, it's negative. We can substitute the magnitude of F right away here, and then we can set these two equations equal to each other. So this has to equal this. And if we set those equal to each other right here, we can solve quickly, hopefully, and get a length or distance of 5.85 meters. This diagram is not the scale, but you can clearly tell that the force is in between the two forces indicated in blue. In this example, we investigate the effect of a UDL, or uniformly distributed load. So, uniformly distributed loads are very common in practice and represent when an object does not impart a single force at a single point, but rather a force that is spread out over a region. There are many examples that we can bring up, but I'll just show you something very simple. Here is a long object of uniform cross-section and density that's sitting on top of a table. It does not apply a single force to the table. However, through this example, we can relate it to that. In this case, it actually imparts what's called a uniformly distributed force. So this force is spread out evenly across the surface. So in this example, what we want to do is take this UDL of 200 newtons per meter. Notice that it is some sort of a density. Newton per meter is a force per length. And we want to replace that force with a single force. I think you can see by symmetry that this force is going to be 3.5 meters along the cross section of the beam, or in other words, half of 7 meters. And that's what you see here, symmetry. Also, we have to find the actual force, its magnitude and direction. Well, the direction is clearly down, but the magnitude can be found by simply using your basic units. We have 200 newtons per meter, and this object is 7 meters long. So the meters cancel. 200 times 7 is 1400 newtons. And that's why you have this 1400 here. So it's very common to do calculations where you have UDLs, but in order to do the physics and to get to some application solutions, it's usually effective to replace the UDL by a point force. Of course, in more advanced situations where you care about what's going along the cross section, then it's important that you retain the UDL structure. So for things like reaction forces, this type of trick is very common. In this next example, we also have a UDL, but this time symmetry is not going to get you the whole way. You need to think more carefully about how the UDL is applied and where it's applied. But we can use the symmetry locally of the UDL to find its position. So firstly, let's talk about the position. Where am I going to place a single force? So let's call that where XA here, so that it produces the same moment as the UDL. Well, the where, we can use the symmetry locally of the UDL. It's going to be halfway across this length. So half of that length is half of 4 meters. And half of 4 meters is 2 meters. Plus the original 7 meters gives us a length of 9 meters. So now it comes down to finding out what that force is. So we can take the force and do a similar calculation with the previous question. Take your 200 newtons per meter and multiply by. So the question is 7 meters, 4 meters, 11 meters. Well, since the UDL is only applied across a length of 4 meters, it would only be meaningful to multiply by the 4 meters length. So the net force there that replaces the UDL is 800 newtons. And it is acting in a downward direction as indicated here with the vector F. Here's one final example that I'd like you to try as an exercise. I should say that if this example were to appear on a test, for example, it would be toward the end of a test, because it definitely has a little twist to it. Right here we have a force that is not orientated vertically. It is at an angle. So the idea is similar to one of the previous examples, replacing 2 or more forces with a single force. And what that means is, how far do I place this force? Let's call that XA from A. And which way does it point? So is it this way, or this way, or this way, or this way, or is it up? Is it down? Can you decide or make a good guess of which one of these vectors would make sense? Well, since this force here originally has a rightward component, the sum of this force and this force is going to also have a rightward component. So these left ones are not possible. Furthermore, these vertical ones are not possible. So somewhere between this vector and this vector is the correct solution for what the force F looks like. So where is it? Well, if you work ahead, and it is a bit of writing, but you can refer to Blackboard for the solution, and it turns out that that force is in the upward direction, as indicated by my answer given to you below. So the answer to this question would be similar to this diagram. So enjoy doing that question. It definitely is on the tougher side, and if you can get the answer right for this one, I'm feeling good that you can do well with all of the exercises that were presented in this unit. Thank you for your time, and take care.